Well, hello and welcome again to Math 315. This is the fourth recording for Chapter 6. And we've looked at split definition functions and how we can check whether one of these things is differentiable. The split definition functions are going to be differentiable everywhere except at the point where we're trying to glue the two functions together. In the previous theorem we said that the function, if it's differentiable, then it must also be continuous. And so when we're checking a function is differentiable, we have to check continuity as well. So I'll do a couple of examples of this, and the first one is here. We've got a split definition function. F of x looks like x if x is negative, and it looks like sine of x if x is positive. And at x is 0, it's just equal to x. We want to show that this is differentiable at x is 0. That's the point where we're trying to glue the two functions together. So here's the solution to this. And here's our function. It's x if x is less or equal to 0, sine of x if x is bigger than 0. And it's worth having a bit of a quick look at a rough sketch of this. So it's looking like this. It looks like y equals x if we're on the left side of the y-axis. And then it turns into a sine function like this. And we have to check firstly for continuity, make sure the two functions at least glue together properly here. And then we have to check for whether it glues together smoothly by looking at the derivatives. So firstly, we have to check that f is continuous at x is 0. So we do that by looking again at limits. So as I look at the limit as x goes to 0 from below, if we look back to the picture here, we're looking at what's happening this way. And if we're going from below, then we're using the part of the function x. So the limit from below of f of x is the limit as x goes to 0 from below of x, and that of course you just plug in 0, you get 0. And that of course equals the value of f of 0. And if we take a limit as x goes to 0 from above, if we go from the other side, then we're looking at sine x. And so we're looking at the limit as x goes to 0 from above of sine x, and again sine of 0 is going to 0 as x goes to 0 from above. And this value equals f of that one, and it equals the limit. So that means f is continuous. So at this point we can say therefore f is continuous at x is 0. And now we check, so we know the two curves glue together okay. Now we've got to check that it's smooth, and to do that we're going to look at the derivatives. So if I look at the limit firstly, just to do it in the opposite order, as x goes to 0 from above, f dashed of x. So if we're looking at the function from the other side, then we're looking at sine x, and I differentiate sine x becomes cos x. And now I take a limit as x goes to 0 from above of cos x, and of course cos of 0 is 1, so this is going towards 1. And then I look at the derivative from the other side. So as x goes to 0 from below, the derivative of the function, now we're differentiating x, and the derivative of x is 1. And so as x goes to 0 from below, the derivative of 1, well, the 1 just stays as 1, so the limit is 1, and these two agree with each other. So that means we can now conclude this function is differentiable at 0. Graphically, it means it glues together and is a nice smooth transition as you move from this curve to that curve. Functions like this actually are quite important. They turn up in engineering when you've got two different processes and one particular process suddenly turns into another process, a little bit like in a washing machine when you go from doing a rinse to a spin and so on. And you want to make sure that there's a smooth transition between the two things going on. And so we're looking at functions. We want to make sure the two things glue together nicely and that it's a smooth transition between the two functions. By the way, and so I mention here in the notes here that note that simply checking that the left and right values of the derivative is 1 That is not sufficient. You have to also check continuity. And as an example of that, we have a look at this example here. We've got f of x is x squared if x is less than or equal to 1, and it's 2e to the x minus 1 if x is bigger than 1. Now, if you just look at the derivatives, if you differentiate x squared, you get 2x, and then you whack x as 1 in, you get 2. If you differentiate this, well, you just get 2e to the x minus 1. E to the x doesn't change when you differentiate it. And you plug in 1, you just also get 2. So the derivatives match, but this function is not differentiable at x equals 1, because if you take a limit of this as x goes to 1, you get 1 squared is 1. And if you take a limit of this as x goes to 1, then you get 2. And the two limits don't match. So this function is not continuous at 1, even though the derivatives match. The two curves don't glue up properly. You might like to draw a picture of this to see exactly what's happening near 1. So the point about this is we need continuity as well as just checking the derivatives. Well, just to have a look at a couple more examples of this. So here we've got this more complicated function. This is x sine 1 over x. And this is that function I mentioned we drew a picture of before. This one goes quite, if you draw this on a graphics calculator, you'll see that it wobbles around, but eventually it's settling in to 0. And we've already seen that this function is continuous. We've already seen in an earlier example that this function is continuous at 0, because if you take limits as x goes to 0 of both of these, you get 0. However, it's not differentiable at x is 0, and that's what we're going to show now. So here's a little proof that this particular function, x times sine 1 on x, if x is not 0, and we make it 0 at x is 0, it is continuous at x is 0. We did that one before. But if you now try and look at match the derivatives, if you look as the limit as x goes to 0 of f dashed of x, then we'd probably better, as you're going towards 0, so if you differentiate this, well, if x is not 0, then we're using this definition, it's x sine 1 on x, so I'm going to differentiate that. Now, using the product rule, you differentiate the first, that's 1, times the second, so I get that function. And then if I copy x, and I've got to differentiate sine 1 on x very carefully. So sine goes to cos, and I need a plus here. So sine goes to cos, and then I multiply by the derivative of what's inside here. The derivative of 1 over x is minus 1 on x squared, because this is x to the power minus 1. So if you differentiate this, you bring the power down the front, decrease it by 1, and then that's minus 1 on x squared. That's where I'm getting this one from. So a little side calculation there. So you copy x, you differentiate sine, becomes cos, and you multiply by the derivative of the inside, which is minus 1 on x squared. Now when you tidy this up a bit, you're going to get a minus. You'll get a sine 1 on x, you'll get minus cos 1 on x, and I've got an x on the bottom. And now you want to take a limit as x goes to 0. Well, this doesn't exist. This doesn't make any sense. This has got no limit as x goes to 0. And as x goes to 0, this doesn't make any sense either. So this limit doesn't exist. So therefore the function is not differentiable. So f is not differentiable. Differentiable at x is 0. This function is not differentiable at x is 0. Even though it was continuous, you can't tell by looking at a picture of this because it just wobbles in towards the origin, but you can't see what's happening near there. But this function turns out not to be differentiable there. Well, a function which is differentiable at all points in some domain is said to be differentiable on that domain. So if it's differentiable everywhere, then at every point inside some domain, some set of real numbers, then it's differentiable on that whole set. So we're going to, by the example here, we'll explain why this function, it's x plus 1 if x is less or equal to 0, and e to the x if x is positive. We want to show this is differentiable everywhere. Show this is differentiable everywhere. Well, here's the question again. So there's the function. Now, away from 0, then all is well, because away from 0, you've either got the function as x plus 1. We know this is continuous and differentiable everywhere. If you're on the other side, if x is positive, then you've got e to the x. This function is continuous and differentiable everywhere. So I don't need to write half a page essay here. I'm just going to say away from 0, f is continuous and differentiable. It's only at the point 0 where I'm trying to glue the two bits together that I have to worry about continuity and differentiability. Away from there, everything works beautifully. So firstly, I've got to check continuity. So I'm going to look at the limit as x goes to 0 from above. That means I'm looking at the function e to the x. Because for x bigger than 0, f of x is e to the x. I take a limit, e to the 0 is 1. And that in fact is f of 0. If you put 0 into the top formula, you get 1. And then you look at the limit as x goes to 0 from below. In that case, you're looking at x plus 1. That's what the function looks like. And you send x to 0, you get 1. So these happily agree. And so by our continuity theorems that we've had, f is continuous at x is 0. The limit exists as you the two limits, the left and right limits, are equal as you go towards 0. Now we're going to see how smoothly these join together, to see if these connect together smoothly. So the limit as x goes to 0 from above f dashed. So if x is bigger than 0, I'm using e to the x. You differentiate e to the x, is the friendly function, differentiates exactly to itself. And as you send x to 0, e to the 0 is 1. If you go from below, then we're using the x plus 1 definition. You take the derivative of x plus 1, you get 1. And then you take a limit of whatever, as x goes to 0, 1 is still 1. So these two agree with each other. So therefore the function is differentiable at x is 0. And their final conclusion, x is differentiable everywhere. Everywhere. And again, you might just like to draw a little picture of this to see what's happening. So what's happening here is if x is bigger or equal to 0, it's our old friend e to the x, which looks like this. And if x is less or equal to 0, then it's a straight line. So it's a straight line that's going like this. So this would be minus 1, this will be 1. And so what we're showing here is that the two functions glue together nicely. It's continuous, and it's actually quite smooth through here. Okay, final example. We're going to consider this function here, f of x is ax plus b if x is less or equal to 0, and it's sine x if x is bigger than 0. And we want to find the values of a and b which make the function differentiable everywhere. Now, I've seen examples a little bit like this before, where we just talked about continuity, where we wanted to make sure these two glued together. Now we want to make sure they glue together smoothly. And here is the solution of this one. So here's our function, f of x is ax plus b. If x is negative, sine x if x is positive. So we've got a sine curve one side and a line the other. Now we need to check firstly for continuity. So I've got to make sure the two curves glue together properly. So if I take a limit as x goes to 0 from below, then I'm using this form, so that's ax plus b. I send x to 0, I just get b. Now, if I look at the limit as x goes to 0 from the other side, then the definition for there is sine of x, and I take that limit, sine of naught is naught. So in order to be continuous, so for x to be continuous, we need b to be 0 in order for this to be continuous. Now we want to make sure it glues together smoothly. So we need to know to show that the gradients match. And again, before I do that, we might just look at a little picture here with this. So what we've got is here, we've now know b is 0, so this has to be a line. So here's the sine curve, and it's got to be a line through the origin. It's got to be some sort of line through the origin. But depending on what the gradient of this line is as to whether it goes together, it glues together smoothly or not. So that's my f, there's x. Okay, so we know b has to be 0 in order for it to be continuous. Now if b is 0, it could be like this, of course. The line could come in like that, and you see it's going to be a sharp corner, and so we don't want that. We want to choose a now to make it go together smoothly. So if I look at the left derivative, so for x less than naught, then I differentiate ax plus b. The derivative of ax plus b with respect to x is just a, and then you take the limit, you still get a. If you're going from the positive side, then you've got to differentiate sine, becomes cos, and you're now letting x go to 0. Well, the cos of 0 is 1, and you want these to match up. So therefore, a equals 1 for f to be differentiable. So the conclusion is, hence, f is differentiable if we take a is 1 and b is 0. So in fact, we needed this to be the line y equals x, or f of x is x, in order for it to glue nicely together with the sine curve. And that's that was the last example for this chapter.